Hello, everyone. My name is Charles. I'm a Marie Curie Fellow at the University of Strathclyde. Today, I will be giving you a broad overview of our work on spotting expansive physical models with geometric movement invariants to accelerate sensitivity analysis for shape optimization. This work is carried out in collaboration with Institute of Marine Engineering at the Italian National Research Council. The motivation of this work initiates as the shape optimization is critical for engineering design. A typical shape optimization pipeline initiates with a CAD tool in which we build over CAD design. This design is later parameterized, and this parameterization creates a design and a search space which will be explored to find an optimal design. Typically, these search spaces are connected with an optimizers. An optimizer first finds a design or design instance in this space, which is then evaluated with the simulation tools such as CFD or FEE. And the outcome of these tools is given back towards the optimization, which help us to propagate through this space and find an optimum design. These pipelines often suffer from high computational cost, which specifically focus towards the optimizers or the design evaluation tools. And this computational cost rises exponentially with the dimensionality of the design space. For example, if a design space is of high dimension, then a large number of designs evaluation will be required for an optimizer to perform an exhaustive design exploration so that a global optima is achieved. There are different approaches to tackle this drawback of high dimensionality, which can be broadly classified as dimensionality reduction or surrogate modeling. In design space dimensionality reduction, unsupervised techniques such as PCA and autoencoders have been widely used. So the main objective for these approaches is to extract the geometric or the important features in the original design space and learn a new basis for the design space whose dimensionality is lower than the original design space. There are also some supervised approaches such as sensitivity analysis. In sensitivity analysis, what we do, we try to learn the sensitivity of the parameters towards the quantity of interest, such as any of the performance criteria, and we learn which parameter is more sensitive. That means these parameters are highly significant towards the quantity, and when you only use those parameters to construct a lower dimensional design space. Surrogate modeling approaches, on the other hand, focusing on bypassing the need for of design evaluation tools like CFD and FEA with the approximation models. These approaches have gained a lot of attention with recent advancements in machine learning and deep learning. Let's talk about some drawbacks, specifically of supervised techniques like sensitivity analysis and surrogate modeling. The reliable training of these techniques for engineering problems, specifically of high dimensionality, requires big datasets. And these big datasets for specific engineering problems are not readily available at hand and therefore has to be constructed. However, we all know that to run a single simulation, a high fidelity simulation, it's itself a high computationally demanding task. And imagine now running such high fidelity simulations thousands of times will still cause the entire pipeline to suffer from the computational complexity. So, the over objective here is to find some properties or some quantity which are closely related to physics but are computationally less expensive to evaluate, and using those such quantities to obtain the sensitivity of the parameters. The first thought that comes to our mind is of the geometrical integral properties such as moments. We all know the physics for specific designs act as a shape signature or a descriptor for that design. It's very closely related to the geometrical integrals, where these integrals are also used to categorize a specific design. So our first thought or our idea was, can we use these geometrical properties to make a preliminary decision on the sensitivity of the parameters? these geometrical integral properties have various applications from in design in computer visions and in physical analysis. They have been widely used for object recognition, shape retrieval, rigid body transformation, and more importantly in physical analysis, where these methods are used in structural analysis, and most importantly in meshless physical analysis, where these geometrical movements act as a basis to represent the shape in governing equation of motion in fluid simulation. So these properties have diverse range of applications. So, what are a geometric movement of a shape? Geometric movements of shape are the intrinsic properties of any geometry, and more importantly, they act as a medium for interoperability between the geometry and the physics. And this was the key point for us to use these movements, or to see if these moments can be used to complement the physics, specifically to drive the sensitivity of the parameters. These geometric moments can be evaluated as Riemann integrals for any geometric domains, and the most commonly used moments is the zeroth order moment, which is the volume of the shape. So these movements can be evaluated at any order. So from the first to of an nth order, these, as we move from the first to the second to the higher orders, we will capture more and more of the geometric properties. Here are some of the representation of the geometry. So for the first order, we will capture some information, and when we move to the second, we will capture more information, and as we will continue moving towards the nth order, towards the infinity order, we will capture more and more information about the geometry. So unlike the physical quantities, most of the physical quantities, these moments are variant to transformations such as translation, rotation, and scaling. So as the physical quantities are, most of the physical quantities are invariant to these type of transformations. So what we have to do, we have to evaluate the invariance of these moments. So for instance, to evaluate the moments which are invariant to translations, what we have to do, we have to take our geometric domain, put it at the center, and evaluate the moments. So once we have a moment, we create a shape signature vectors which contain all the moments up to a specific order, up to a nth order. And then we use this shape signature vector to evaluate the sensitivity of the parameters. And this, as I said, this shape signature vector can also be regularized in order to have the invariance against the uniform scaling. So once we have over all moments, what we have to do, we have to perform the sensitivity analysis to learn the sensitivity of the parameters. So in our case, what we did, we used the global variance-based methods, the Sobel's method commonly used, and with this method gives us the sensitivity index, which is a numeric value with respect to geometric moments for each parameter. So the parameter having the sensitivity index greater than a predefined threshold, it's more sensitive compared to the other parameters. So let's say we have an original design space, we sample that design space, we evaluate the geometric moments, and we evaluated the sensitivity of our parameters. And then we use the most sensitive parameters whose sensitivity index is higher than the given threshold. So we evaluate only that set of the parameters, and get the lower dimensional design space. We sample that design space, we evaluate their actual performance criteria, we construct our surrogate models. Once we have our lower dimensional space and the surrogate models, we connect it with the optimization, perform the shape optimization to optimize our design. So in our case, as a test case, we use a DTMB54 naval shape model, which is widely used in the research community. So this model was parameterized using a global shape modification function, which provide something like freeform deformation on the shape approach, and that design was parameterized with using 27 dimensional parameter, which is considerably which creates considerably high dimensional design space. And our objective here is to optimize the designs for a calm water wave resistance coefficient, which is an important criteria specifically in ship design. And this wave resistance coefficient represents the wave making when the ship moves through the water. So as the design was parameterized with 27 parameters, so this creates a 27 dimensional design space. So to initiate the proposed methodology, we sample this design space with 9,000 uniformly distributed design using a Monte Carlo method. Here are the results of the sensitivity indices of the parameters when sensitivity analysis are performed with respect to wave resistance coefficient CW, which is shown here in orange, and with respect to the fourth order geometric moment, which is shown here in blue color. So the parameters which are highlighted with red rectangles are the parameters which are both sensitive with respect to the CW, which is the performance criteria, and with respect to the fourth order geometric moment. The most interesting thing here is that all the parameters which are sensitive with respect to the fourth order geometric moments are also sensitive towards the wave resistance coefficient. So only the one parameter, the parameter 17, here you can see that it has a sensitivity index greater than 0.05 with respect to wave resistance, but less than 0.05. So this is the only parameter which is sensitive with respect to wave resistance coefficient CW, but not sensitive with respect to the fourth order geometric moment. So at the end, we get a six-dimensional subspace when we perform sensitivity analysis with geometric moments, MI4, and a seven lower dimensional subspace when we perform a sensitivity analysis with respect to wave resistance coefficient. So once we perform over sensitivity analysis and we get over sensitive parameters, so we construct two different design spaces. The first design space is constructed is the lower dimensional design space, which is constructed with only the sensitive parameters which are sensitive with respect to wave resistance coefficient, and the second subspace is constructed with the parameters with only the parameters which are sensitive with respect to the moments, in our case the fourth order geometric moments. Within this subspace, as I described in my previous slides, that we perform the surrogate modeling in these subspaces, and then with the surrogate modeling and these subspaces, we run over shape optimization. Here you see the optimized designs performed, original and the optimized designs obtained after running the shape optimization along with their wave resistance coefficient values. The interesting thing here is that from these, the optimal design that we obtained from these two spaces has only 0.64% percentage difference between their wave resistance coefficient, so they both have almost a similar performance. But the critical thing here is to know that the computational cost. So the computational cost of performing the sensitivity analysis with respect to wave resistance coefficient in a typical or in a traditional way took us about 375 hours, whereas when we perform the same pipeline with respect to the moment, it took us only 9.5 hours. That's a huge difference that we get in terms of computational cost, and we're still able to achieve the same results in terms of our performance criteria. So this shows that this proves experimentally that the moments, first of all, can be used to complement or to replace, to say, the wave resistance coefficient, which is an important performance criteria, and to achieve the similar type of optimization results. So in conclusion, we can say that the moments which are closely related to the wave resistance coefficient are physical quantity, and we use these type of computationally less expensive properties to complement and to replace the physical quantities, at least to drive the sensitivity of the over parameters. As the future works, we would like to test this approach for different types of test cases, for different type of shapes, which are parameterized with different type of parametric models, and they're for different type of performance criterias. We would like to evaluate this sensitivity specifically towards this type of moment. With this moment, we have theoretically proven in our work that this moment is very closely related towards the wave resistance coefficient. We would like to, because currently we have investigated this correlation experimentally, but we would like to investigate theoretically how these two properties, the moment and the wave resistance coefficients, are closely linked together. And finally, we will like to integrate these moments not only for dimension reduction as we have done in this work, we would like to integrate these type of properties into the machine learning model, into the surrogate models, specifically which will be informed, which will specifically in a setting of some type of physics informed learning. So these are the funding properties, and at the end of this session, I would like to take any questions if there are any. Thank you very much.